review here. Last time we talked about the effects of viscous flow. We said we're going to focus on internal flow, specifically completely filled conduits. We talked a little about a number of things. And we said for completely filled conduits, we said there's a difference between the models we're going to use to describe that viscous flow for laminar flow and turbulent flow. We use the Reynolds numbers to predict whether the flow is laminar or turbulent. Talked about how do we compute the Reynolds number, and we said how does that help us? Well, again, our goal is to try to describe the loss associated with the viscous flow. And that can take the form of the pressure loss, head loss, energy loss, power loss. Just depends on what we multiply or divide by to get that value. My cat is going to help us today. This is Izzy, our guest star. You can hear her jingling and meowing. Anyway, let's see what she does. Maybe she'll leave us alone. All right, so again, our goal is to try to describe the Darcy friction factor, a function of the Reynolds number and the roughness, epsilon over d. We'll see that table today. Okay. Now, let's see here. So, where we left off, we said we're going to pick up today talking about some example problems. Right, so this is from the Changle and Symbolic text. That's what we're working out of. We said there's a couple of different kinds of problems that we'll encounter. Let's look at 839 first, and then maybe we'll talk about, we'll work on 835 also. We'll get both of those done today. Okay? So 839 is kind of the simple version, or a simple type of problem that we'll encounter. Oof, here we go. When we're talking about trying to estimate pipe friction, and so again, this is Changle and Symbolic. Yeah, Changle and Symbolic. Third edition, number 839 is what we're going to look at here first. We've got water. They've given us a temperature. That temperature will tell us the properties of the fluid. The density of liquid water is going to be reasonably constant, but it will vary some with temperature. Viscosity, though. Viscosity will vary significantly with temperature. Now, if these numbers are not given in the problem statement, we can go to the property tables in the back of our text and look those up. Again, given the temperature, you'll be able to go look up saturated liquid water will have essentially the same properties as liquid water at that temperature. So, we've got water flowing steadily in a 30-meter long, 5-centimeter diameter horizontal pipe made of stainless steel. And they've given us a volumetric flow rate. They want us to determine the pressure drop, the head loss, and the pumping power required to overcome the pressure drop. Okay. Trying to figure out how to manage my space here. Probably move my laptop out of the way. Let's just move the laptop. I'm learning as we go. All right. So we've set up a number of example problems in class before. Let's talk about, given, what is this? This is 8. We said this is 839. Okay. Example. What have we been given here? We've been given that we have water. They've given us 15 degrees C. They've given us the density. It's a metric unit problem. About 1,000 kilograms per meters cubed. We said that's a fairly standard value, but they've given us a specific value, so we'll use it. Viscosity, mu value, 1.138 times 10 to the minus 3. Those are kilograms per meter and also per second. So we've got water flowing steadily in a 30-meter long, so I've got a length here of 30 meters. It's 5-centimeter diameter. It's stainless steel. That's going to be important a little bit later. Up till now, we really haven't cared what kind of conduit the material is flowing through. This is stainless steel pipe. And they've given us a volumetric flow rate. That's volume per time of 9 liters per second. They want us to find a few things. And they're essentially asking for the same stuff. It's just in different ways of asking. They want us to find the pressure drop. They want us to find the head loss. Right? The pressure drop, by the way, I would suggest that's P sub L, pressure loss. The head loss, they want us to find the head loss. They want us to find the pumping power. How much power input will we need to overcome the pressure drop? Right? And so, simple diagram, nothing complicated. I've got a stainless steel pipe, 5 centimeters, 30 meters long, flowing at 9 liters per second, water coming in. Okay? So that's what we're looking at. Alright. So now that I've got the problem statement, I'm going to set the textbook aside. I say, alright, well, how do we find these quantities? Well, the pressure loss, I was going to start with the energy loss, but that's okay. We can start with the pressure loss. Pressure loss is going to be the energy loss multiplied by the density. And the energy loss is going to be the Darcy friction factor times epsilon over d times essentially the average kinetic energy, v squared over 2. Right, this is the density times the energy loss. Right, so the energy loss is going to be the Darcy friction factor, epsilon over d, v squared over 2. Multiply by density, and that gives you the pressure loss. Now, as we've said before, this Darcy friction factor is going to be a function of what? Well, the Darcy friction factor is a dimensionless quantity. We said it's a function of a couple of other dimensionless quantities. We learned that in the previous chapter. It's going to be a function of the Reynolds number, and it's going to be a function of epsilon over d. And I've made a mistake here. I apologize. This is length over diameter. Here, this is epsilon over d here. So the Darcy friction factor is a function of the Reynolds number and epsilon over d. The pressure loss is going to be a function of length over diameter. We call this the relative length. We call this the relative roughness. All right. Now, hopefully I don't make too many more mistakes. I'm sure I'll make a few. I'm sure you'll point them out in the comments if I make a whole bunch. That's okay. Let's see. Where do we go from here? Well, we know the Darcy friction factor to find the pressure loss. But let's see what else is unknown here. I do know the density. I do know the length. I know the diameter. I do not know the average speed of the fluid flow. So I do need to find that. And what are some ways to find that? Well, based on what I have, we could find that speed using the volumetric flow rate. By the way, if you're joining us, if you're a guest, not in my class, and you're joining us, you may use Q. There are a lot of texts that will use Q for flow rate. In our text, we use volume V with a dot above it. That's V dot. That's volumetric flow rate. So anyway, and of course we can find the area by pi times diameter squared over 4 times the speed. And we know this, now I can find that speed. Alright, so speed is 4 v dot divided by pi diameter squared. Okay, and so we can find some things then. Let's see, so I can find V now. I think that's all, at least I've got all my unknowns here except for the Darcy friction factor. So let's find Darcy friction factor, right? I guess we could go ahead and let's go ahead and find the speed here while we're here. Now, I will mention the diameter. They've told us it's 5 centimeters stainless steel. Now, we could go look up I should acknowledge that the actual stainless steel is probably not going to be exactly 5 centimeters internal diameter. We could easily go look up commercial stainless steel. If we knew properties of the stainless steel pipe, if we knew the schedule, the thickness of the walls, then we could go look up the actual diameter and use that to compute here. Since they didn't tell us much about this piping, we're just going to have to assume that 5 centimeters is a reasonable value for the diameter. Okay, and so let's just find that here. 9 liters per second. That is, if I convert that to cubic meters, that should be 1, 2, 3. I believe that is 9 cubic meters per second. Okay. So, with that, we're going to say then that the speed is equal to 4 times 9 cubic meters per second divided by pi divided by 0.05 meters squared. Now normally, and have your calculators out, guys. Those of you who have had me in class before know to have your calculators out. I apologize, my phone screen is cracked, but I think it'll work for us. So that's going to be 4 times, I'll move this centered so you can see it, 4 times 0.009 divided by, where's my pi button? Divided by shift pi, and divided by 0.05 squared. So I'm getting 4.58, we'll say 4 meters per second. I sincerely hope I don't make mistakes as I do these computations. I'm sure I will. That's okay. That's the reason I have you guys help me out with computations, because I will typically make a mistake there. But let's see how we do. All right. Got speed? Okay. Now we need to know the Darcy friction factor. That's going to be a function of the Reynolds number and epsilon over d. Well, let's go look at this epsilon value. The fact that we know it's stainless steel is enough to give me the epsilon. Where do we get epsilon values? Well, that's in your text, or we can go find a trusted source online somewhere, but your text is a really good trusted source. In Chapter 8 of your text, or whatever text you're using, somewhere in there, it'll talk about when it talks about pipe friction, you'll have an equivalent roughness value for different piping. We have stainless steel. So I've got an epsilon value for stainless steel of 0.002 millimeters. Stainless steel, 0.002 millimeters. That is, in our text, that is table 8-2. In the 3rd edition, that is page 368. Okay. Now we need to now figure out our Reynolds number. This is going to be page number 1. We do need to find the Reynolds number. This is the simple problem because I can actually find the Reynolds number. It's a little more challenging when I can't find the Reynolds number. In this particular situation, I can't. For epsilon, Reynolds number is going to be rho v d over mu. That's a formula you want to memorize. Have on your sheet of equations that you can use on the test. Okay. That's my timer. So we're going to pick up there, start the next video because I'm going to get cut off in 15 minutes. So loud pop here.